The Libyan sun beat down relentlessly on Gambit Airfield in June 1942, but it wasn't the heat that troubled Flight Lieutenant Neville Duke. It was what waited high above, at 22,000 feet. Up there, where the air grew thin and engines gasped for breath, German Bf-109F fighters ruled the skies. The Spitfire McPhee, once the pride of the Battle of Britain, was now embarrassingly outclassed in the one factor that decided survival in air combat: altitude. The numbers painted a grim picture. A Messerschmitt Bf-109F4 could climb to $20,000 feet in about 7.5 minutes, while the Spitfire MKV took nearly 9. 2 minutes might not sound like much until you're the pilot watching enemy fighters forming up 3,000 feet above, ready to dive, strike, and escape before you can even react. The Germans called it boom and zoom, and it was devastating RAF squadrons across North Africa. Wing Commander Ian Gleed recorded the issue in his 244 wing combat reports. His pilots often faced Bf-109s that would simply climb out of range when the battle turned against them. British pilots struggled upward, their Rolls-Royce Merlin 45, engines screaming and superchargers whining, while the Germans effortlessly gained altitude, circling like hawks. The aerial equation was simple but deadly. Whoever held the height held the fight, and by the summer of 1942, that wasn't the RAF. The Spitfire's service ceiling was around 36,500 feet, but its performance dropped sharply above 20,000. The Merlin 45 engine, superb at low altitudes, faltered in the thin desert air where most combat occurred. The Germans learned fast. They climbed above 25,000 feet before engaging, forcing Spitfires to burn precious fuel and arrive overheated and exhausted. Squadron leader Brendan Paddy, Finucane of 602, Squadron watched 3 of his pilots fail to return from a patrol on June 12, 1942. Reports from survivors echoed the same story: ambushed from above, too slow to climb, forced to dive away to survive. Dive away. The words felt like defeat. The Spitfire, once the symbol of air superiority, was now fleeing battles because its engine couldn't perform where it mattered most. It wasn't a question of bravery or skill. RAF pilots in North Africa were among the best, veterans of the Battle of Britain and Malta convoys. But experience meant little when engineering left you 2,000 feet below your enemy before a shot was even fired. Many pilots began requesting transfers back to Europe, where lower altitude fighting favored the Spitfire's strengths. By mid-1942, the crisis had reached the top. Air Vice Marshal Arthur Coningham, head of the Desert Air Force, needed an answer. His fighters were being dominated vertically, and no amount of tactics could fix an engine that couldn't breathe at altitude. Rolls-Royce was developing new Merlin versions, but they were months away. The men needed help immediately. Unbeknownst to Coningham, that solution was already forming in the mind of a single mechanic about to commit what Rolls-Royce would call heresy. Flight Sergeant Henry "Ginger" Lacey wasn't an engineer. He was a fitter, trained to maintain airframes, not engines. But in North Africa, those lines blurred. When spare parts took weeks to arrive and sand got into everything, you either learned every inch of a Spitfire or watched pilots die because you didn't. Lacey had rebuilt Merlin engines countless times. That kind of familiarity breeds dangerous confidence. During pre-flight checks in July 1942, he noticed something odd about the boost pressure gauge. The Merlin 45's limit was 29 pounds per square inch, marked in red. A danger zone pilots were forbidden to cross except in emergencies, and then only for seconds. But Lacey had seen these engines after brutal dogfights, pushed past the red line, and they hadn't exploded the way the manuals warned. Rolls-Royce's documents were clear and frightening. Exceeding boost limits could trigger detonation, an uncontrolled explosion that would shatter pistons, crack heads, and turn a 2,000 horsepower masterpiece into molten wreckage in moments. Every pilot knew that red line meant life or death, not just for the enemy, but for himself. But Lacey had his doubts. He'd been around enough engineers to know one thing. They always built in safety margins. They would test an engine until it broke, find the exact point of failure, and then set the operational limits safely below that to allow for wear, manufacturing differences, and human error. It was good engineering practice, but what if Rolls-Royce had been too careful? What if the true safe limit was higher than the manuals said? The thought kept bothering Lacey as he watched Spitfires return from missions, pilots angry, their fights ineffective. One evening, over a cup of lukewarm tea in the dispersal tent, he shared his theory with Flight Lieutenant James "Johnny" Walker. Walker listened carefully, then pointed out the obvious problem. Even if Lacey was right, even if the engines could handle more boost, pilots couldn't access it. A mechanical governor on the throttle physically blocked the lever from going past the point that created +9 psi boost. It was a built-in safety barrier, impossible to bypass by accident. To exceed it, someone would have to deliberately modify the throttle assembly. Walker didn't need to spell out what that meant. Tampering with an aircraft's engine controls without authorization wasn't just against orders. It was a court-martial offense. The Air Ministry had strict rules about modifications. Everything had to go through official testing, documentation, and approval. What Lacey was suggesting ignored all of that. It wasn't science, it was intuition and a mechanic's instinct that the engineers back home had played it too safe. But Walker had already lost 2 wingmen in 2 weeks because their planes couldn't climb fast enough to reach the enemy. He had seen them die helplessly, diving away from Bf-109s above them. So when Lacey asked if he could test the idea on Walker's own aircraft, the answer came instantly. Do it. And if it works, do it to every Spitfire here. Official channels had achieved nothing. Maybe it was time to try something unofficial. The Rolls-Royce Merlin wasn't just a machine, it was a masterpiece of controlled violence. 12 cylinders of metal precision centered around a single-stage, single-speed supercharger, a centrifugal compressor spinning at 30,000 RPM, driven directly from the crankshaft by gears. Its purpose was brutally simple. Force more air into the engine than nature would allow. More air meant more oxygen. More oxygen meant more fuel could burn. More fuel meant more power. That supercharger was why a 27-liter Merlin could produce over 1,400 horsepower instead of 600 if left unpressurized. Boost pressure measured how much extra pressure the supercharger added above normal atmospheric levels. At sea level, air pressure is about 14.7 psi. So when the Merlin showed +9 psi on the gauge, it was pushing air into the intake manifold at about 23.7 psi total, nearly 60% more than the atmosphere provides naturally. That compressed air got hot, very hot, which was why the Merlin used an intercooler to cool it before it entered the cylinders. Without cooling, hot air became less dense and defeated the purpose of compression. The science of combustion explained why Rolls-Royce set strict limits. Inside each cylinder, the fuel-air mixture was supposed to burn smoothly outward from the spark plug. But compress it too much, heat it too much, and disaster followed. Detonation. Instead of burning in waves, the entire mixture exploded at once. The pressure spike was instant and violent enough to punch holes through pistons or crack cylinder heads. Engineers called it knocking because of the metallic, hammering sound it made, a warning that the engine was seconds from destruction. The Merlin 45 originally ran on 87-octane fuel, later upgraded to 100-octane as supplies improved. The octane number measured how much compression the fuel could withstand before detonating. With 100-octane fuel, Rolls-Royce determined that +9 psi was the safe limit, leaving room for fuel quality and mechanical differences. Beyond that was the danger zone, where detonation could kill the engine, but that was theory. Real engines, built by real people, all varied. Some might knock at plus 10 psi, others might run smoothly even at plus 12 psi. Rolls-Royce had no way to know which engine was which, so they set one rule to protect the weakest ones. It was statistically smart, but tactically frustrating. It meant that many perfectly good engines could make more power than the regulations allowed, and then came the biggest problem of all: temperature. A Merlin running at +9 psi on a cold morning in Scotland behaved very differently from one straining under the Libyan sun, where air temperatures hit 45 degrees C. Hotter air meant hotter combustion chambers and a greater chance of detonation. The official limits couldn't account for every climate or condition, so Rolls-Royce issued one universal number, safe everywhere, but limiting in many places. To enforce it, the throttle gate itself physically prevented pilots from pushing further. Could barely hide the grin beneath his oxygen mask as he shut down the engine. Advancing the throttle past the +9 psi position was physically impossible, blocked by a simple metal stop. Often just a bent tab or bolt. Removing it took barely 10 minutes with ordinary tools. But doing so meant every pilot who pushed the throttle forward would be betting his life that his specific engine, at that temperature, with that fuel, could survive boost levels Rolls-Royce swore would destroy it. That was the risk Lacey was ready to take. He waited until after the evening patrol landed and the pilots headed to dinner. Walker's Spitfire MKVB, serial BR546, still clicked as the hot metal cooled. The job itself was almost insultingly simple, which was perhaps why no one had tried it. It seemed too crude to matter. Lacey opened the access panel on the port side and traced the throttle linkage with his flashlight. There it was, the stop welded to the quadrant, blocking the lever beyond +9 psi. It wasn't locked or bolted in a complicated way, just secured with safety wire. Lacey snipped the wire, removed the stop, and carefully filed the mount smooth so no one could tell it had ever been there. 8 minutes, but that was only half the fix. The Merlin's intake system had a second line of defense, a relief valve that vented excess pressure to prevent overboost. It opened automatically around +9.5 psi, bleeding off air to protect the engine. Lacey couldn't leave that as is. He could remove it or adjust it. He chose adjustment. If his math was wrong, the valve might still save the engine. Working under the cowling by flashlight, he removed the inspection panels and found the spring-loaded valve. 3 turns on the adjustment nut increased the spring tension just enough for the valve to stay closed until around +112 psi, about 3 pounds higher than before. That meant 20% more power. There was no visible sign of tampering unless someone took the assembly apart or tested the valve pressure. The boost gauge would still function normally. It would just show numbers beyond the red line pilots were trained never to cross. Lacey closed the panels, tightened the screws, and stepped back. Walker's Spitfire looked unchanged, but it was now capable of performance that would shock anyone who believed the official specs. The danger was real. If the engine detonated, piston failure would be instant, connecting rods punching through the crankcase, oil spraying everywhere, even the propeller breaking free if the crankshaft shattered. Walker would have seconds to react, maybe none at all if it happened in combat. And if it did, Lacey's career would end with a court-martial. Unauthorized modification causing the loss of a plane or a pilot meant prison, but Walker had agreed. To him, the Germans above were more dangerous than a Merlin running hot. At dawn, Lacey stood by the dispersal hut and watched Walker climb into BR546 for patrol. Neither man told anyone. If it worked, they'd know soon. If it didn't, it wouldn't matter. Walker ran his pre-flight checks carefully, eyes lingering on the boost gauge. The Merlin started with its usual deep growl. Everything felt normal, which was either reassuring or terrifying. At 06:20 hours, he lifted off and began a wide climbing turn over the Mediterranean, heading out to sea, just in case the worst happened. At 5,000 feet, everything was stable. He eased the throttle forward. The needle passed the red line for the first time in his flying career. From 10 psi, nothing happened. 11 psi, still smooth. At pleasant 12 psi, the plane came alive. The surge of power pinned him to his seat. His climb rate shot up, where a standard MKV managed roughly 2 to 800 feet per minute. His gauges now read nearly 3,400. The Spitfire that had been obsolete was climbing like the next generation MiG-9, which wasn't even in full service yet. At 15,000 feet, he leveled off and ran checks. Full throttle at plus 12 psi gave higher airspeed and steady temperatures. The morning air was cool, helping keep the Merlin calm. A timed climb from 15,000 to 20,000 feet took just 6 minutes and 40 seconds, almost 2 minutes faster than before. That meant a 2,000-foot advantage in battle. He kept climbing. 22,000 feet, 24,000, 26,000. The altitudes that had belonged to the Luftwaffe for months. Still no trouble, no knocking, no vibration, just raw, flawless power. Then, over the coast, he spotted 2 faint contrails, enemy fighters returning to base. Normally, he'd avoid them. Engaging on equal height was suicide. But not today. He shoved the throttle forward to 112 psi and pulled into a climbing turn no MiG should ever have managed. The German pilots saw it too, the impossible sight of a Spitfire climbing like a hawk. Their contrails veered sharply away. Walker didn't chase. He'd already proved the point. The modification worked. It hadn't just fixed the problem, it had rewritten the rules. When he landed at 07:55 hours, the engine still running smooth as silk, Lacey was waiting nearby, trying and failing to look casual. That he would not ground any aircraft performing safely in combat. Walker shut down the Merlin and climbed out, his face blank until he was close enough to speak quietly. "Every Spitfire in the squadron," he said. "Tonight." "Do it to every aircraft we have," Lacey nodded. That night, with the help of 2 trusted fitters, Sergeants Mills and Patterson, he worked non-stop under the desert stars. By dawn on July 23, 1942, 16 Spitfires of 145 Squadron carried the secret modification. They agreed on a cover story, routine throttle cable maintenance. Technically true, just not the whole truth. At breakfast, the pilots were briefed in hushed tones. Push past the red line. Ignore the gauge. Trust the engine. The day's combat report sounded like fantasy. Flight Lieutenant Jeffrey Wellham engaged a Bf-109F at 24,000 feet and outclimbed it, something thought impossible. Pilot Officer David Cox chased a German fighter trying to escape vertically and matched it all the way to 28,000 feet. Overnight, the balance had shifted. German pilots who had ruled the upper altitudes suddenly found Spitfires diving on them from above. Word spread fast, as it always did in war. Within days, ground crews from 601 Squadron appeared at 145's dispersal, asking careful questions about recent performance improvements. Lacey tried to dodge, but the results were too obvious. Pilots talked. Over drinks in the mess, they compared climb rates and altitudes. By the end of the week, 601 Squadron had made the same changes. Then 92 Squadron, then 417. The modifications spread through Gambit and beyond, like a quiet rebellion, a mechanical contagion. Every engineering officer faced the same moral equation. Follow the rules and lose men, or break them and save lives. Most chose the latter. Group Captain Hugo Lacey, the station commander at Gambit, discovered the truth in mid-August. Reports from several squadrons showed identical, impossible climb performance. He called in the engineers. They didn't lie. They explained exactly what they'd done. Lacey understood the stakes. Officially approving such modifications would violate Rolls-Royce specifications and invite disciplinary chaos. But the results spoke for themselves. So Lacey did what clever officers do, nothing. He filed no reports, issued no orders, and made sure higher command never found out. The silence was his approval. Not everyone shared his pragmatism. At Tarkali Airfield in Malta, squadron leader Reginald Grant discovered similar modifications and was horrified. A strict by-the-book officer, he immediately ordered them reversed. His mechanics obeyed by day and quietly reinstalled them by night. The next morning, when pilots praised the aircraft's performance, Grant assumed they were exaggerating. The mechanics said nothing. In London, the Air Ministry remained blissfully unaware through August and most of September. Reports of improved performance were chalked up to better tactics and increased experience. No one in Whitehall imagined that dozens of squadrons were defying engineering orders en masse. That illusion shattered in late September. A modified Spitfire suffered an engine failure over Sicily and made a forced landing in friendly territory. The pilot lived, and the aircraft was recovered for inspection. Investigators found the throttle modification immediately. Within hours, a top priority order was sent across the Mediterranean. All unauthorized throttle modifications were to be reversed at once, and any ground crew caught making them would face court-martial. The order was acknowledged and ignored. Engineering officers signed the paperwork, then did absolutely nothing. The pilots kept flying with forbidden boost levels, and combat success stayed high. The facts were undeniable. Nobody wanted to give up a change that was saving lives, no matter what London decreed. Air Commodore Raymond Kershaw, commanding 204 Group, faced the impossible. He had direct orders to enforce the ban, but also hard data showing that squadrons with modified aircraft suffered far fewer losses at altitude. His pilots trusted the engines. His engineers guaranteed their safety. And most telling of all, after 2 months of use, not a single Merlin had failed from overboosting, so Kershaw quietly informed his superiors that he would not ground any aircraft performing successfully in combat. That enforcement would take time, then quietly made sure it took as long as possible. The Air Ministry responded by sending a technical investigation team, led by Squadron Leader James Tate, a Rolls-Royce liaison engineer who had worked on Merlin engines since the war began. Tate arrived at Gambit in October 1942 with orders to inspect the modified aircraft, document the damage, and prepare evidence for disciplinary action. But what he found defied every expectation. The engines were fine. Tate personally examined 12 Merlins that had been running at plus 12 psi for more than 200 hours. He pulled cylinder heads, expecting cracked pistons and scored walls, but found only normal wear for desert operations. Bearings and crankshafts were within tolerance, showing no unusual fatigue. The engines that should have torn themselves apart were running perfectly within limits, just limits Rolls-Royce refused to admit existed. The team widened its study. Maintenance logs, pilot interviews, and temperature readings told the same story. When flown with skill and managed properly, engines running at plus 12 psi remained stable. Morning missions benefited from cool air, which offset the thermal strain. In hotter afternoon patrols, pilots learned to ease the throttle and manage their mixture. Tate's preliminary report, dated October 18, 1942, was a masterpiece of understatement. He admitted the modifications broke official procedure and that Rolls-Royce's limits were grounded in sound reasoning, but he also couldn't deny the proof before him. The engines were safely producing power levels the manuals said were impossible. His recommendation was cautious but revolutionary: conduct controlled testing to determine if the official limits were overly conservative. That single sentence lit a bureaucratic firestorm. Rolls-Royce's engineering director protested that field mechanics had bypassed safety testing. The Air Ministry's maintenance branch warned that allowing such behavior would undermine all technical authority. But Air Marshal Arthur Tedder, commanding RAF Middle East, cared about one thing: his squadrons were finally holding their own against the Bf-109s. A compromise was reached in November. The Air Ministry would not approve the modifications, but it would stop punishing them. Squadrons could continue operating at higher boost levels under a new, deliberately vague phrase: combat emergency power. It wasn't approval, but it was protection. Meanwhile, Rolls-Royce began a crash test program at Hucknall in December 1942 to see if the mechanics were right. Engineers ran Merlin 45 engines at +12 psi for long durations, measuring everything: cylinder head temps, exhaust gas, bearing wear, vibration, fuel flow. The results were both vindicating and embarrassing. The engines handled the power easily, provided good fuel was used, and pilots avoided max boost for more than 5 minutes. By February 1943, Rolls-Royce quietly issued new specifications: maximum continuous boost, +12 psi with 100-octane fuel. Emergency combat boost, +16 psi for up to 5 minutes. The numbers matched what Lacey and the others had already proven months earlier in the desert. The once illegal modification became official procedure. Future Merlin engines incorporated these lessons directly. The Merlin 66, introduced with the Spitfire Make 9 in mid-1943, was built to handle higher pressures. It featured stronger connecting rods, redesigned pistons, and upgraded bearings, all informed by the unauthorized experiments in North Africa. It was officially rated at +18 psi for combat and +25 psi for emergencies, boost levels that had once been considered suicidal. Those desert mechanics had changed how Rolls-Royce understood its own machines. The policy impact reached beyond Spitfires. The Air Ministry established new systems for testing field innovations, recognizing that frontline crews sometimes discovered truths the engineers missed. Future technical orders began allowing controlled trials for unapproved modifications that showed promise. The wall between lab engineers and field mechanics cracked, if only a little. Henry "Ginger" Lacey never received recognition. His name appeared in no citations, no honors, no official history. Acknowledging him would mean admitting that an unauthorized fix had outperformed official design. After the war, he returned home to Lancashire, repairing motorcycles in quiet obscurity. When asked about the war, he'd only say, "I worked on Spitfires," and leave it at that. Johnny Walker survived with 12 confirmed kills and a Distinguished Flying Cross. In his memoirs, he credited the modification with saving his life 3 times, allowing him to outclimb German fighters that would have otherwise destroyed him. He mentioned engine work by ground crew, but avoided naming names, protecting those who had risked everything. The legacy of that act of defiance changed aviation forever. Engineers learned to separate absolute mechanical limits from conservative operational limits, to design systems that could adapt rather than restrain, and to formalize feedback from combat experience. Modern fighter jets still carry that philosophy. Their engines have multiple power settings: normal, combat, emergency, controlled by electronic limiters that pilots can override if they must. The same spirit born in a dusty Libyan revetment lives on in every modern throttle. In October and November 1942, Spitfires over El Alamein climbed into battle at boost pressures that didn't officially exist, flown by pilots who trusted their mechanics more than their manuals. The mechanics had been right. Sometimes the man with the wrench knows something the man with the slide rule doesn't.